Okay, this is lesson 2.2, derivative rules, tangent lines, non-differentiability, and rates of change. So the expression d dx means to differentiate with respect to x. And the most common derivative is going to be our d dxy, which is usually written dy dx. So dy dx. Okay, so our first four derivative rules we're going to look at are the power rule, constant rule, scalar multiple rule, and the sum rule. Okay, the power rule says that our derivative with respect to x of x to the n is equal to n times x to the n minus 1. Okay, so I take my power, I drop it in front as a coefficient, and then I reduce the power by 1, and that's my derivative. Okay, so as a reminder that the slope of the tangent line is our derivative of the function. Okay, and that this, essentially, if a derivative exists at a point on a curve, then it's differentiable. Okay, we saw this power rule idea essentially happen in example 1 of lesson 2.1. So if you look back at that, you can see how it kind of forms. Okay. Second is our constant rule. If c is any constant, then d dx of c equals 0. Okay, so if I have just a constant hanging out there, our derivative is 0. That's also seen in example 1 in 2.1. Next is our scalar multiple rule. If c is any constant of d dx of c times f of x, we can pull that c out, that value, and then take our derivative, which we'll see a little bit here. Okay, and then last is our sum rule. So if I have d dx of f of x plus g of x, then my derivative is just going to be the derivative of f plus the derivative of g. So essentially I can break up terms and take the derivatives of each piece. Okay. So let's look at some examples here. Example 1, I have f of x equals x to the 4th. So I've got my variable to a power. So using that power rule, it says that my derivative is going to be equal to 4 times x to the 4 minus 1 power. So I'm going to rewrite that. So my f prime of x equals 4x to the 3rd. And that's it. All right, so that's going to be that slope of my tangent line. Okay, that gives me that equation. Okay, number 2, I've got y equals x to the negative 2/3 plus 3. So I'm going to take the derivative of each piece. So piece 1 is my x to the negative 2/3. I drop that power, so it's my constant, or my coefficient, x, and then I'm going to have negative 2/3 minus 1. We'll come back and simplify that in a second. Okay, and then because of the sum rule, I can take this as two separate pieces. So next I'm going to take the derivative of 3. 3 is a constant. Okay, so my derivative of a constant is 0. Okay, and I said we're going to go back and we're going to simplify my negative 2/3 x to the negative 2/3 minus 1. Okay, so my y prime is equal to negative 2/3. Okay, and my x, so now I need to do negative 2/3 minus 1. Okay, I can think of that as doing negative 2/3 minus 3/3, so that they have the same denominator. Okay, let's go pick a different color. So we're going to take, I'm going to work out over here. So negative 2/3 minus 3/3. Same denominators. So I just need to worry about the numerator. So negative 2 minus 3 gives me a negative 5/3. So we have negative 2x, or negative 2/3, x to the negative 5/3, and then my plus 0. Okay. If I'm just taking the derivative and I'm not going farther with this, I would leave it like this. Don't have to worry about kind of the simplifying. If I am going to have to like use it later on, it might be helpful to simplify. Okay. And to do that, that means we're going to rewrite that negative 5/3 power. Okay. So this is going to look like y prime is equal to negative 2 over 3 times the cube root of x to the 5th. Okay. That's using exponent properties. Okay. The main one essentially here is that if I have x to the m over n, that's equal to the nth root of x to the m. Okay, so that's a property that we're going to be using quite a bit to rewrite exponents with fractional exponents as radicals. Okay. The other thing I used here is that if I have a negative power, I rewrite it in the denominator and make it positive. Okay. So that's number 2. Okay. You kind of saw this in example or in 2.1 also, kind of looking at problem number 2 or example number 2. Okay, next, number 3, I have h of t equals 5 minus 1 over 2t cubed. Okay, this time I'm going to simplify this. So I'm going to rewrite that t to the cube so it looks like a power, not in the denominator. Okay, so my 5 is going to stay there. My 1/2 is going to stay chilling there too. And then my t cubed is going to turn into a t to the negative 3. Okay, because that allows me to apply my power rule so we can take our derivative. Okay, so take my derivative. I'm going to work from the left to the right. So we're going to take the derivative of positive 5, which gives me a 0. Okay, and then we're going to take the derivative of negative 1/2 t cubed. Okay, so based on essentially our scalar multiple, I can kind of set this 1/2 off to the side and take the derivative of my t to the negative 3. Okay, so to do that, I'm going to drop my negative 3 to be my coefficient. T to the negative 3 minus 1. Okay, now I can simplify. So my h prime of t is going to be, I'm going to do my math here, 0 minus, I think, is just make it negative, right? So I have a negative 1/2 times a negative 3. So that's going to give me a positive 3/2. Okay. And then I've got t to the negative 3 minus 1. So we get t to the negative 4. Okay. So that's the derivative of 5 minus 1 over 2t to the 3rd is equal to 3/2 t to the negative 4th. Okay, or 3 over 2t to the 4th power. Okay, next, number 4. I have f of x equals 5 over 2x cubed. Okay, so I'm going to rewrite this with things kind of simplified out a little bit. Okay, so 2x cubed, all of that is cubed, so I'm going to apply the cube to the 2 and the 3. So we'd get 2 cubed and then x to the third. Okay. Want to simplify it a little bit further. So 5 over 8, because that's 2 times, or 2 to the third power. And then I've got my x to the negative 3. Okay, we rewrite that power. Okay, so now I can take my derivative. Okay, the 5/8, that's that constant, right? That's kind of just chilling there, that coefficient. Okay, so 5/8 times, drop my negative 3, x to the negative 3 minus 1. So then we get 5/8 times negative 3, so negative 15/8 times x to the negative 4th. Okay, or I can rewrite it as negative 15 over 8x to the 4th. Okay. Okay, so example 1, we saw that power rule. Example 2, we saw the power rule and the constant rule. Okay, example 3, we saw the power rule, the constant rule, and that scalar multiple, and essentially the sum rule also. Okay, and then example 4, we saw the power rule and the scalar multiple rule, but also rewriting. Okay, so we're going to be practicing these derivative rules. And essentially what these rules allow us to do is to take the derivative without having to go through the limit definition. Okay, so I don't have to rewrite and simplify. We can use these ideas. And ultimately, if you forget what they are, you can always go back through to that limit definition and use that. Okay, with derivatives, we can take derivatives multiple times. Okay, because it's the derivative of a function is another function, right? My derivative of x to the 4th gave me 4x cubed. That means we can repeat this process. Okay, and these are called our higher order derivatives. So we have first derivative, second derivative, third derivative, fourth derivative. Okay, and just kind of our different ways to write these. So so y prime, y double prime, y triple prime, and then we essentially have like y fourth prime. Okay, kind of just the notation, and then we have like f prime, f double prime. Okay, and then dy dx. Okay, and then we've got kind of where we add those superscripts. Okay, so that we can denote it. So we're going to look at example 5 here. It says for f of x equals 1 over 2 times the cube root of x squared, find f prime of 1 and f double prime of negative 8. So what that means is we're going to be plugging in 1 and negative 8 after we take the derivative of our f of x. So first off, I'm going to rewrite that f of x so that we have not a radical and our powers aren't in the denominator. Okay, so our 1/2 is just going to kind of chill there. My cube root of x squared, okay, I'm going to rewrite that as x to the negative 2/3. Okay, the power becomes the numerator, the index, or what root I'm taking becomes my denominator. Okay, so we're going to look at this as 1/2 x to the negative 2/3. So now I can take my first and second derivatives. Okay, so first derivative, 1/2 is going to stay there, kind of just chill. And then we're going to drop our power, so our negative 2/3, x to the negative 2/3 minus 1. Okay, so now I'm going to simplify. Okay, so I have 1/2 times negative 2/3. okay? Because I have a 2 in the numerator and a 2 in the denominator, those divide out and make a 1. But I'm left with that negative, so I'm going to get negative 1/3. And then my x to the negative 2/3 minus 1. So I'm doing negative 2/3 minus 3 over 3. So we're going to get x to the negative 5/3. Okay. I'm going to leave it like that so that we can take our second derivative, which means we're taking now the derivative of negative 1/3 x to the negative 5/3. Okay. So our f double prime of x is going to equal, okay, it's already set up for us, so that negative 1/3 is going to sit out front. Okay, times we drop our power, so negative 5/3, times our x to the negative 5/3 minus 1. Okay, I'm going to simplify this time. I'm just going to have to multiply negative 1 times negative 5 and get a positive 5. 3 times 3 is 9. So we get 5/9. Next, my x to the negative 5/3 minus 1. Really minusing 3 over 3. So I get x to the negative 8/3. I'll write that f double prime again. Okay, so we found our derivatives, our first derivative and our second derivative. And now it wants us to plug in values. So f prime of 1 is going to equal negative 1/3 times 1 to the negative 5/3. Okay. 1 to the negative 5/3, this would also look like this. So negative 1 over 3 times the cube root of 1 to the 5th. Okay. 1 to the 5th power is still 1, and the cube root of 1 is 1, so we get negative 1/3. Okay, and then f double prime of 8 is going to equal 5/9 times negative 8 to the negative 8 over 3. Okay. Then you could plug that into the calculator and get your value. Okay, I'm just going to leave it just like that for now. Okay, so that's kind of a way and a reason why we would take our derivative is to find values. Okay. Right, so since the derivative of a function gives us a slope formula for tangent lines to the graph of the function, the derivative can be used to find equations of tangent lines. Remember, those tangent lines are the lines that essentially touch our curve once, and our curve slope matches the tangent slope. Okay. And then sometimes we'll want to find a line perpendicular, right? So at 90 degrees to the tangent line at the point of tangency, which is called our normal line, okay? So if we ever see something say the normal line, that means perpendicular, okay, right? So at 90 degrees. And then whenever we see something saying like something about equations of tangent lines, that means we need to find the derivative and then do some stuff. Okay. So for, well, let's talk about the normal line again. The normal line, right, its slope is 1 over the slope of the tangent line. Okay. So if I know the tangent line, I can find the normal line. If I know the normal line, I can find the tangent line. Slopes. Okay, so our example 6, it says find the equation of the line tangent to the graph of f of x equals 4x to the 5th minus 3x squared plus 5. Okay, so at the point 1, 6. So our first thing we're going to do, okay, is to find f prime of x. Okay, so we're going to find our derivative because that's going to help us get our tangent slope. Okay, so if f of x equals 4x to the 5th minus 3x squared plus 5, we're going to break it up into pieces. Okay, so I've got my 4x to the 5th. So let's write this over here. So f prime of x. Okay, so 4x to the 5th. I've got my 4 times my 5 times x to the 4th, right? I subtract 1 there. Next, I've got my negative 3x squared. So I'm going to do minus 3 times 2 because I dropped that power. X to the 2 minus 1, so 1. And then last I've got that plus 5. It's a constant plus 0 for the derivative. Okay, so I'm going to simplify this. So I get 20x to the 4th minus 6x. So our derivative is 20x to the 4th minus 6x. Okay. Step 2 is we need to find this, like this gives us the equation of the slope. Okay, we need the actual value. So we're going to find f prime at 1. Okay, and I get that 1 from our 0.16 that was given to us. Okay, so f prime of 1 means we're going to be plugging 1 into our derivative. So I'm going to do 20 times 1 to the 4th minus 6 times 1. Okay, so 1 to the 4th power is still 1, so 1 times 20 gives me 20. 6 times 1 is 6, so I still have 20 minus 6, which gives me 14. Okay, so this 14 is my slope of my tangent line. Okay. But ultimately, this says we want to find the equation of our tangent line. Okay. So last step is to write our equation. Okay. And we're going to use point slope form. Okay. So y minus y1 equals my slope times x minus x1. Okay. Unless it says, like, write it in slope-intercept form, okay, we want to keep it in point slope form because then we're just plugging values into this. We're not trying to rearrange it or anything like that, okay? So we're going to plug in these values. So y minus, let's go over here, my y1, so that's my 6 here, so minus 6. Okay, is equal to my slope, so my 14. Okay, and then x minus 1. So my x and my y1 values come from the point given to me. Okay, and then we find that tangent slope by finding the derivative, which then gives me the slope. Okay, and we're going to leave it like this. I'm not going to distribute my 14 and move my 6 to the other side. I'll just leave it as is. Okay, so whenever something says find the equation of the line tangent to the graph, okay, we're going to find the derivative, evaluate it at the point, and then write our equation. Okay. So part 7 here says find an equation of the normal line to the same curve at the same point. Okay. Well, the normal line means that our slope of the normal is equal to -1 over the slope of our tangent. So for our problem on number 6, our slope of our tangent was 14. Okay, so we get -1 over 14. So that's my slope. So now we're just going to plug it back into that equation. So y minus 6 equals -1 over 14 times x minus 1. Okay, I'm just trying to kind of color code this so you guys can see kind of what's going on. Okay, so we're going to be asked sometimes write the equation of the line tangent to the graph, or write the equation of the normal line. Okay, so that's going to give us find the derivative, evaluate, point slope form. Okay, next, non-differentiability. So when a derivative does not exist, right? We looked at in Unit 1 when limits exist. Okay, and those are important because they kind of give us an idea of when things aren't going to have a derivative. Okay, so here are 5 examples. We have a hole, we have a jump, we have a vertical asymptote, we have a sharp turn, and then a vertical tangent. Okay, so for each of these, there is no derivative at x equals 1. Can't happen. Okay. Our first 3, our hole, our jump, and our vertical asymptote are all discontinuities, right? They're not continuous functions. Okay. Whereas like a sharp turn or a vertical tangent, they are continuous. Okay. They have essentially those limits and it's considered continuous. Okay. If a function is not continuous, it is not differentiable. Okay, so that's my first 3. And then a function may be continuous and still not be differentiable, which is my last 2. Okay, so we're going to look at a couple examples and find the x values where f of x is not differentiable and give a reason for each. So our first one is f of x equals the absolute value of x. Okay. And ultimately, I think thinking about what the graph looks like is the easiest here. So for the absolute value, right, I plug in a value and it's going to be positive. So like when I plug in -1, I get +1. When I plug in 0, I get 0. When I plug in +1, I get +1. Right? So my absolute value is going to look like that. Okay. Different color here. So right here at x equals 0, okay, we have a sharp turn. So x equals 0. Our reason is a sharp turn. Okay, because it's that like pointy, right? Like it doesn't like smoothly go. It like essentially hits 0 and then turns. Okay. Next one, I've got a piecewise function. F of x equals x when x is less than or equal to 0 and x when x is greater than 0. Okay, so I'm going to graph this one as well. Okay, so it's x squared when x is less than or equal to 0. So 0 squared is 0. -1 squared is 1. We'll do another one over here at -2 is +4. So we kind of have a parabola there, right? It's half a parabola. Okay, my other side, I've got x when x is greater than 0. So at 0, we get 0. At 1, we get 1. At 2, we get 2. Okay, so that one's going off that way. I want to make my quadratic look a little bit better. There we go. So essentially we have that quadratic coming in and then it shoots off into a linear function at x equals 0. Okay, so we have a sharp turn. Okay, next, number 10, I've got f of x equals x squared when x is less than or equal to 0, and x squared plus 1 when x is greater than 0. Okay, so I'm going to graph this one again. So my x squared when x is less than or equal to 0. Graph that. Okay. I'm going to switch colors so we can see it a little bit better. My x squared plus 1 when x is greater than 0. So when I plug in 0, 0 squared plus 1 is 1. Open circle there. Plug in 1. 1 squared plus 1 is 2. Okay, and so this one's going to kind of go up like that. So for this one, we have a jump at x equals 0. Okay, so this one's not continuous, right? Okay, next, 11. I've got f of x equals x over x times x minus 1. Okay, every time I see these rationals, I always think, what can I divide out? Okay, so in this case, I've got an x in the numerator and x in the denominator, right? So those divide out and make a 1, which is great, which also means we're going to have a whole there, right? So we have a whole at x equals 0. Okay, but left over, we still have this x minus 1. Okay, right? My f reduced of x is 1 over x minus 1. So I can't divide that out. So we're still going to have something happen, which is our vertical asymptote at our x equals positive 1. So wholes happen if I can divide stuff out. Vertical asymptotes happen if I can't. All right, so if I were to graph this, we'd have a whole at 0 and then a vertical asymptote at 1. Okay. And then number 12, I have f of x equals the cube root of x. Okay. And look at the graph again. Okay, if I plug in 0, I get 0. If I plug in 1, I get 1. Negative 1, I get negative 1. Okay. And then this one, if I plug in 8, I get 2. Okay, so 3, 4, 5, 6, 7, 8. Same thing, 1, 2, 3, 4, 5, 6, 7, 8. I plug in negative 8, I get a negative 2. So this graph kind of looks like this. Okay. And kind of the spot in question, okay, is right here, okay, at 0. And what happens there is we have a vertical tangent. Okay, so if I were to zoom in really close, right there at 0, then my slope would be 0. Okay. So if I were to draw like in a line here, my tangent line, it would have a slope of 0. Okay, so those are kind of our different things that can happen, right? Holes, jumps, vertical asymptotes, sharp turns, and vertical asymptotes are when our function is not differentiable. I can't take a derivative there. Okay. Next, rate of change, right? We talked about rate of change being, we can look at the average rate of change, which is the slope between 2 points, and it's found without using a derivative. So using our algebra, something you've learned as soon as you start looking at lines. It's essentially that rise over run, right? So the average rate of change equals our slope, which equals the change in y over the change in x, or my y2 minus y1 over my x2 minus x1. Now that we know about differentiation, we can use that to find that instantaneous rate of change. Okay, we talked about back in Unit 1 that instantaneous rate of change before calculus, we essentially kind of have to find the average rate of changes close to the value we're looking for. Now, we can find the derivative and plug in that point value. Okay, so the instantaneous rate of change is the slope at a single point. It's usually found by using a derivative. Okay, so we're going to look at an example. So 13 says, if f of x equals x cubed plus 2x, find the average rate of change from 10 to 30. So x equals 10, that's going to be my x1. X equals 30, it's going to be my x2. So our average rate of change is equal to f of 30 minus f of 10 all over 30 minus 10. Okay, so f of 30 means I plug 30 into my equation. F of 10 means I plug 10 into my equation. Okay. And f of 30 is 27,060. F of 10 is 1,020. And I got my 30 minus my 10. Simplify all of this. Okay. I get 1,302. So my average rate of change from 10 to 30 for this function is 1,302. Okay. Next, number 14, it says, if f of x equals x cubed plus 2x, find the instantaneous rate of change when x equals 10. So 10 is the value we're going to be plugging in. So first, we need to find the derivative of our f of x. So f of x equals x cubed plus 2x. So f prime of x. Okay, so my x cubed, drop the 3x squared, reduce the power by 1. Okay, my 2x, so plus 2. Okay, and then this x, remember, has a 1. So I could do 2 times 1. And then, let's write that out so you can see it. And then x to the 0. But remember, anything to the 0 power is 1. So what we really have here is that f prime of x is equal to 3x squared plus 2. So that's our derivative, right? So now to find the instantaneous rate of change, we're going to plug in 10. So f prime of 10 is equal to 3 times 10 squared plus 2. And I'm going to simplify. So 10 squared is 100. So I've got 3 times 100 plus 2. So I get 302. Okay, and we can say our instantaneous rate of change right there. Right, so our instantaneous rate of change is 302. Okay. So if something asks for the average rate of change, we use our y2 minus y1 over x2 minus x1. Okay. If it asks for instantaneous rate of change, we're going to take the derivative.